comfortable, stay warm. We're going to have quite the show for you. Tonight, we have two contestants. First contestant, the king of calculus, the tangential terror, the numerical ninja, Euler's boy himself, Dr. Kelly Cline. And his opponent for tonight, gotta remember all the names, the Duke of Data, the Viscount of Visualization, the Differentiation Caucasian. He's not integrate, he's integrand, Dr. Eric Sullivan. And I'm Ted. Tonight's debate will focus on what the most important mathematical model of all time is. Now, in my younger days, a lot of people considered me to be the most important mathematical model of all time. Age, it seems, has caught up with me. So when we're talking about a mathematical model, what we're really talking about is something that we can use to answer fundamental questions. And that's really what a model is. A model is a representation of a thing. And a mathematical model is a representation of a thing that uses math so that we can ask and answer questions about the nature of the thing that we're studying. Now, the two models that we have presented tonight, I think, without a doubt, are definitely in the top 3 models of all time. So we're going to have a heck of a debate. As is customary, we're going to do a coin flip to see who goes first. Dr. Sullivan, as the challenger, I'm going to have you call it in the air.
Heads.
Head.
I would like to defer.
All right, so the most important mathematical model of all time is this equation right there. Force equals mass times acceleration, often known as Newton's second law of motion. With this equation, this mathematical model, we can understand and predict the motion of everything. Almost every object in the universe can be understood with this elegant, beautiful equation. So let's talk about the history of this. 2,500 years ago, back in the good old days of ancient Greece, this fine gentleman here, this is Pythagoras, one of the very first mathematicians that we know of, who had this wonderful vision, this amazing dream that mathematics is the key to understanding the universe. Everything that there is can be understood through mathematics, through the language of mathematics. And he had this amazing vision of that, and wasn't able to get too far. He worked out some things about some triangles and some harmonies and some notes, but he left this grand vision of what could be, that perhaps we could find mathematical laws to explain everything that there is. And this is the culmination of that dream that finally allows us to understand this. With this equation, we can understand why things move and how things move, and that's what the universe is made of. It's made of objects in motion, whether we're talking about the orbits of the stars or the path of a following raindrop, the motion of a galloping horse, the vibration of an eyelash, or the wind blowing across the hillside right here. All of this, and the movement of an atom attached to my DNA. All of these things can be understood with this beautiful, elegant, powerful mathematical model. The first step toward it came a couple 150 years after Pythagoras. Aristotle gave us this idea of force. Aristotle considered the question, why is it that things move at all? And he answered, well, forces are what make things move. And so that's where we get this idea from. But his idea of what forces were and how they affect motion were not actually very accurate. If Aristotle was right, then a force would cause things to move, and so a steady force would cause things to move steadily, but that's not how things really work. If I drop a stone, it moves faster and faster. The force of gravity is constant, and yet it gets faster. If I throw a baseball, the baseball doesn't stop moving the instant it leaves my hand. The force stops with my hand, and yet the baseball keeps going. So we get one of these concepts, the idea of force, from Aristotle, so that's great. But it took another almost 2,000 years before Galileo was the first person who really began to reckon with the concept behind this amazing idea. He performed a thought experiment. He said, what would happen if you had a perfect sheet of ice and you slid a stone across that ice? And if the ice was tilted uphill and you cast the stone upon it, it would go slower and slower as it went uphill. And if it was tilted downhill, the stone would go faster and faster. And so if it was just perfectly flat, that stone would go forever. It would go at a constant speed in a straight line. And Galileo realizes that motion is natural for things. You don't need a force to keep things moving. Once something is moving, it will keep moving. Forces change motion. They cause forces to change motion. So if I drop a stone, the acceleration is what is caused by the force. The constant force of gravity causes it to get faster and faster at a constant rate. So after 1 second, the stone is falling at 10 meters per second, and then it gets faster as things go. And this allows us to finally understand the motion of objects. This was 50 years after Galileo. Newton took everything that Galileo had done and codified it and put it in better mathematical language and showed that this forces, this acceleration could be either getting faster or getting slower or changing direction. And with that understanding that force can act in different directions and how it can bend paths, Newton could then explain everything. With this simple equation, he could then explain everything from the falling of the apple to the orbit of the moon around the Earth. And he wanted to understand the orbits of the planets around the sun. And this began the science of physics. And it is such an incredibly powerful mathematical model. So let's look at this just a little bit. So force equals mass times acceleration. So, okay, mass. My car has a mass of about 2,000 kilograms. When I get a green light, it can accelerate forward at about 2 meters per second squared. So I can multiply those two together. 2,000 for my mass, 2 for my acceleration gives me about 4,000 newtons. So I can use this to calculate the force that my wheels must be exerting to push my car forward. But that's not the most interesting part. The interesting part is, what if I know the forces in advance? Then I can calculate the acceleration, and then I can predict how it's going to move. I can predict what things will do before they actually move, and that's the interesting thing. A mathematical model should allow us to predict the future, to see what's going to happen before it happens, and then shape our decisions based on that, make choices, because we know what's going to happen. Newton uses this to solve the mystery of why is it that when the planets orbit the sun, when Mars goes around the sun, it doesn't go around the sun in a perfect circle. It goes in kind of a squashed circle we call an ellipse. Why does that happen? Newton explains that and explains beautifully exactly why the planets orbit the sun in the way they do. And then we take that law, we take that beautiful mathematical model, and then we can use that to explain the motion of everything else. So here's something I like to talk about. So my background comes from astrophysics, so I got to talk about that. We can predict the future. I can tell you things that will happen billions of years from now using this equation. Right now, our Milky Way galaxy, great big giant spiral disk of stars containing hundreds of billions of stars, is on a collision course with the Andromeda galaxy, also containing several hundred billion stars. And 4 billion years from now, these two galaxies will collide. What's going to happen when these two galaxies happen? Well, we can tell by using this equation. What we do is we take each galaxy and break it into a bunch of pieces, because you got lots of stars all over the place. We can calculate the force of gravity on every piece of each galaxy. Then, using force equals mass times acceleration, we can then calculate the acceleration of each piece, and then predict how each piece will move, and then recompute our forces. We put this on a computer with some beautiful algorithms, and all of a sudden I can create a computer simulation which allows me to look billions of years into the future and show you now what will not happen until long after our sun has burned out. We can run a computer simulation, let's see, there we go, of what's going to happen. So here's our Milky Way galaxy spinning there, and we're going to pull back here, so not too far in the future, a billion years. And then we know where the Andromeda galaxy is, we know its velocity, and we know how the force of gravity works, so we can calculate what those forces are. and how these things will interact with each other. Galaxies are mostly empty space. Space is big, and stars are not nearly as big as space. And so when these things collide, we can then compute exactly what will happen and see that, well, they're going to be pulled closer and closer together, and when they come together, they're going to splash against each other, mostly pass right through each other, and then gravity will pull them back again. There are a couple of satellite galaxies moving around from each other. We're now looking 5 billion years into the future. That's about as long as our sun has left in it. And as it happens, these two galaxies will come together and eventually merge into one big uber galaxy. And so we can see what will happen 7 billion years in the future. This mathematical model is so powerful, it can look so far into the future and tell us what will happen. That is absolutely incredible. We can do this in more, that's a little esoteric. For more practical sorts of things, we can use this to design useful technologies and things. If I want to design a better airplane wing, well, we can take force equals mass times acceleration and describe the forces that happen when you have a fluid, like the air moving, and the forces that can exist on it with some viscosity and pressure. And we put that, and then some wonderful mathematicians put that together, and we call it the Navier-Stokes equation. It describes how fluids move. And so I can try out a shape of a potential wing, break the air into thousands of blobs of air, calculate the force on each one, use force equals mass times acceleration to calculate the acceleration of each blob of air, and then throw a computer into all this, and then we can run simulations and explore what happens when you have different shapes of wings, different shapes of aircraft. We can use this to develop all sorts of technologies. This is wonderful. If I want to design a tall building and say, what happens when an earthquake happens? Will this be safe or will it fall down? Force equals mass times acceleration allows us to do that. Suppose I want to design an artificial leg so that someone can run a marathon on it and not have it bend or break or anything, and survive and do well and see how it will respond to all those forces. We use force equals mass times acceleration to calculate how it will move in response to that. Design a bridge over a river. There's a picture of a bridge that once fell down in a river because it was not designed very well. Now we can explore different designs, see how they respond to different forces, different winds on things. This is an amazing piece of mathematics that allows us to explore, to understand, to create, to build things that we've never built before, because we have a mathematical model which allows us to predict what will happen. And that's incredible. This is the most important mathematical model in all of history because it allows us to understand, to predict the world around us. It applies to almost every object in the universe, from things as small as an atom to as large as a galaxy, to the rippling of the curtain right here in the wind today. All these things can be understood through this amazing mathematical model. It's practical, basis of engineering, all this sorts of things, and used throughout the sciences. Whether we're trying to understand the velocity, the flow of blood in your arteries, or earthquakes moving through the Earth's crust, the trajectories of black holes, or look into the distant future to see what will happen when the Milky Way galaxy collides with Andromeda. That's amazing. That's powerful. That's incredible. That's wonderful. That's why force equals mass times acceleration is the greatest mathematical model in all of history. Thank you.
Well, okay, that was cute. So let's get to the best model now. So I'm Eric Sullivan. I teach math, I teach data science, I teach statistics, all the really fun stuff here at Carroll College. Those are all the classes that you're going to take from myself and from Ted, and I guess that guy too, from Dr. Cline. The goal was to talk about the greatest mathematical model of all time, and I cannot deny that force equals mass times acceleration is a pretty darn good one. I mean, billions of years into the future, nobody's going to be there to see it, but sure, yeah, we can predict it. That seems pretty cool. I want to take a step back, though. Just for a slide here, one step back. What is a mathematical model? So, you may not actually be familiar with the term. This is not somebody like Vanna White who's standing there modeling for you. Right? This is an algorithm, this is a function, this is an equation that encapsulates reality in some way. You somehow have reality, so you mimic reality. It's useful in predicting the future. Dr. Cline would have you believe that its most important use is billions of years into the future. Sometimes, though, reality is really, really complicated. So you can create a mathematical model that is really complicated and impossible to solve, or you can create a really simple mathematical model that captures most of reality. And I'm actually going to throw a bone to Dr. Cline here. F equals ma is a really simplified version of motion. Really, really simplified. It's actually much more complicated than that. If you build a really complex model, you might be completely screwed. Right? You might not be able to solve it at all, and then what's the point? And so mathematicians and scientists have to find this happy medium as to, do they build a model that's really complicated that captures everything? Or do they build a model that is a little bit more simplicity, that is really close to reality? So the one that I'm going to talk about, that I claim is one of at least the top two, most important mathematical models, is this really simple idea at the bottom of the slide here, that in populations, the growth rate in the population is proportional to the amount that's in the population. So stop and think about this for a second. If you look at E. coli, so the picture I've got there is like a microscope slide of some E. coli. If you zoom in on those little devils, they're nasty, gross little devils, but they're multiplying. About every 20 minutes, they're doubling. And so their growth rate is proportional to the current amount. That's the mathematical model. And we can watch them double, and over the first few hours, not a whole lot happens, but oh my goodness, as time goes on, the number of E. coli bacteria just grows and grows and grows. And this turns into what we all know as exponential growth. So the mathematical model here is the growth rate is proportional to the amount that you have. And E. coli is a really great simple example. So if we keep doing this out into the future, right, this gets really, really steep really fast. And unfortunately, we will have more E. coli bacteria than there are atoms in the observable universe in about a week. So this model doesn't work. Right? The model's good, but it doesn't really work. It works for short times. Oh, there we go. All right, so let's talk about some others before we talk about how we can break it. All right, so growth rate is proportional to current amount. So carbon dating is another example. All right, when do we use carbon dating? Shout it out. Archaeology, yeah, archaeology. Oh, good, our archaeologist in the back here. Our geologist, I'm sorry, in the back, is saying, yes, archaeology. All right, carbon dating. Let's see, spread of a virus. The change in the infected population is proportional to the susceptible population. I don't know, where have we heard that before? Boy, okay, so another one. How about the change in the current balance in your investment account is proportional to the amount that's currently there? Right? The interest rate is what controls how, some of you are looking at me like, whoa, is that how that works? Yes, that's actually how that works. All right, so when does this model fail? Well, what you didn't realize is that this is actually not just one way. I'm not going to deliver. You have to discuss. So, when does this fail? Talk to each other. All right, let's hear a few. Let's hear a few. When does this fail?
Environmental factors
What environmental factors?
outside that actually affect like the growth, like kill half the E. coli. or whatever.
Oh, okay, so you've got some other competing species in there eating some of the E. coli. Okay, awesome. What else?
Overpopulation.
Overpopulation. So you've got these E. coli sitting in a petri dish. They reach the edge of the petri dish. They have no more room to grow. Now what do? Okay, what else?
When the banks fail.
When the banks fail. Thanks, Steve. That's a lovely thought.
Where's your money?
So in other words, you're saying when your interest rate stops being what you predicted it might be. I guess. So when food runs out, when space runs out, when your interest rate changes, when competing factors such as hunting or reproduction change, this model actually does fail. That's okay. Dr. Cline chose not to tell you about any of the failings of F equals MA, of which there are many. He chose not to tell you about them. All right, so let's address some of these failings head on. So let's actually take the lack of resources and say, hey, what if we were to run out of resources? And say, hey, my change in population is no longer just proportional to population, but now I've introduced, let's see, does a laser pointer work? That little m there, that m that's in that equation is the carrying capacity for the population. The amount of E. coli that you could put inside the petri dish. Well, if your population, let's look at this. If your population's really close to that m, that fraction is about 1, and this stuff in parentheses is about 0. If you're at about the carrying capacity, your change is about 0. Does that jive? Does it seem okay? Okay. If your population's a long ways from the carrying capacity, that fraction's really small, and so this stuff in parentheses is about 1. Well, therefore, your change in population is proportional to about how much you have. Therefore, you've got exponential growth. So early on, you should have exponential growth, and later on, you should have something that levels off. One small little mathematical tweak, we have another beautiful model. This model, called the Logistic Model, works really well for populations that will eventually level off. Let's look at another one. I've got bobcats and rabbits here. Because I happened to find a picture of a bobcat chasing a rabbit. This is really the exact same model. Right? The population of bobcats is going to be affected by the population of rabbits. If there's a lot of rabbits and the bobcats are really low, the bobcats are going to eat a bunch of rabbits and they're going to get more and more bobcats. Rabbits are going to fall. If the rabbits fall too far, the bobcats are going to drop accordingly. It's really the exact same model. The change in population is proportional to how much is there. All right, let's try another one. The classic SIR model, the spread of virus through a population. So the S, the I, and the R. The S is the susceptible population. Who's susceptible to the virus? I is who's infected or infectious. And R is who's recovered or no longer susceptible. And, oh, there we go. It's the exact same model. The change in susceptibles is proportional to how many susceptibles are there, which of course depends on how many infected people they ran into without their mask. The change in infected is proportional to how many infecteds are there, which of course also depends on how many other infecteds and susceptibles they ran into. So really, in conclusion, this really simple model, with some minor tweaks, is really flexible. It can model all sorts of different population dynamics, not just E. coli, but really human populations as well. Works really well for short time, can be tweaked and fiddled with and played with to give all sorts of great models for a really long time. A truly great mathematical model. Maybe the best one, but that's for you to decide.
Well, I'm convinced by both of you. So I don't know how I'm going to vote. All right, so this is the part where we open it up for questions for you guys. It's big and wide open here, and y'all are far away. So if you have questions, you can raise your hand. We'll point at you, and then we need you to shout so that we can hear down here, and we'll try and answer your questions. Let's start with right there.
Yeah! What are some failings of F equals MA? Like examples.
You heard the question?
There we go. The question is, what are some failings of F equals MA? So F equals MA works wonderfully for almost everything, and I did say almost. The biggest failing happens when things are moving fast, approaching the speed of light. And then all of a sudden things get more interesting, and we need Einstein's theory of relativity to understand objects that are moving very quickly. It also can fail when we look at the very, very small scale. Notice I mentioned an atom. I didn't mention an individual electron, but when we talk about individual particles, then they start to behave less like particles and more like waves, and we have quantum mechanics going on. And so again, we have to modify our mathematical model. It doesn't completely go out the window, but now I have to use that, and I have to change it and put together the Schrodinger wave equation to describe how waves of probability can describe individual electrons. I'd say those are the principal ways that we have to model this, and places where we have to extend it and make tweaks and changes to it in order to model things beyond where it's useful. Very good. Yeah.
My question was answered.
Oh, okay. Yeah. Yeah.
Mr. Sullivan, so or Dr. Sullivan, my mistake. Does your model apply to like cosmic phenomenon and such, or phenomena, I guess is the correct word? Like, you cited a lot of examples of living things and populations. How about inorganic and like stuff going on in the natural, like in space or something?
No. Great question. No. The model that I have here, this one, the change in the amount is proportional to however much is currently there. Most of the time is used for living organisms. Most of the time.
I want to add something to that, because the honest truth is that equation where the rate of change of it is proportional to the amount we have is actually used by astronomers a lot. If I'm trying to understand light moving out of the atmosphere of a star, if you got a little bit of light moving, that tends to trigger other atoms to give off more light, and that very equation, and some slightly modified versions of it, are used to understand the distribution of light energy produced by glowing balls of gas like stars.
Stop helping him!
Thank you. I learned something new. This is great.
Which model can be used to save more lives?
Mine. The question was, which model can be used to save more lives? I'm simply going to point at a slide. This particular slide, so I want to add something to this, and I left it off the slide intentionally. We saw this, whenever the COVID stuff started. The blue curve here was meant to be the susceptible population in a population that's being hit by a virus. And if I put a little horizontal line across there, right at the top, maybe you can see the laser pointer, right up here, we were seeing a little horizontal line a little bit lower than the top of that blue curve, where the hospital capacity was. I'm sorry, I said susceptible, I meant the infected, right? The infected here, right? And if we have the hospital capacity on there and we exceed the hospital capacity, well, this model can predict when that's going to happen. And in fact, that's exactly what we were doing when we were trying to figure out, okay, let's squash the curve, let's lower the curve, whatever words we were using back then. We were actually talking about the SIR model and how to move the number of infecteds down low enough so we didn't completely overwhelm the hospital system. So which one can save more lives? Well, I guess eventually F equals MA is going to kill everybody. We're doomed. But in the short term, this one. You got more to add?
Sure. Seat belts. Motion. We can understand and predict motion, and motion can be dangerous. So when we're designing cars, when we're designing airplanes, and we want to make them as safe as possible, using F equals ma, we can figure out those things like airbags and seat belts, which can save lots of lives.
Like commonly by regular people and not you guys.
What do you mean, you guys? What is that?
Smart people.
So, all of these people, good.
I think we all use these implicitly. You know, we have scientists and engineers who develop these things, and then even when, if you don't know that you're using these models, you're still using those models. You're using things created by other people using these models. These are both used by everybody pretty much every day. Cool.
Other questions?
So I'm kind of torn because, I mean, was it Einstein who said the most powerful force in the universe is compound interest? But apocryphal, better than apocalyptic. All right, so at this point, we traditionally do our vote so that you, the audience, get to decide who is the winner of our first pseudo-annual outside math debate. Are we doing? Okay, so we're going to do this. Old school, new school? We're going to do this in a cool way, I guess. We don't have fancy voting machines. Those things can be audited. We have a decibel meter. So what we're going to do is we're going to say, by voice vote, and that means be as loud as you can, you need to tell us who you thought won. So, let's see. Do we have an independent observer?
Independent observer? Kelly?
Yeah. You get to be within 6 feet. All right. All those who believe that Dr. Eric Sullivan won this debate, make it known now. Whenever you're ready. All right, all those who believe Dr. Kelly Cline won this debate, make it known now. All those who believe that mathematics of its own is its own reward, and everybody's a winner.
Linear algebra.
And we have the results. Yep. Congratulations, Dr. Cline. Congratulations, Dr. Sullivan. Thank you all for coming out here on a Thursday night when it's not snowing to enjoy math with us. We're going to try and do these things more frequently as we go forward. Some of them will be outside. We're looking at December for the next one, so keep your eyes open. Thank you for coming.